Hello everyone, welcome to the third experiment in lab 2, lab of strength of material. So our experiment for today will be study of stress state in a curved bar subjected to diametrically concentrated tensile force. So basically, if you go to the last experiments for 1 and 2, we had a straight bar and we applied tensile force and we studied the stress and strain and modulus of elasticity and also Poisson ratio. The difference for this experiment will be is that the curved bar instead of straight bar. The objective is to determine the stress state in the curved bar and also to compare the experimental result with the theoretical calculations. And by the way, this manual is available in Blackboard. This is page 91 in the manual, and this figure shows our curved bar. So we are applying a force of P, tension force, from both sides. So this section area, this cross section area, as you see in this section here, will have both values of stress, one for direct stress force over area and another one coming from bending moment. So because of that, as a conclusion, you will find that the stress distribution will be combined between the two of them, two stresses. Our sample or our specimen is a curved bar. It's semicircle. So we have the R1 is the outer radius, R2 is the inner radius. So R1 capital and R2 capitals are the outer and inner radius of the curved bar. R capital 0, this is the average or the mean radius or the center line of the sample, and we have 2 points, point A and B, for applying the force, and also we will measure the stress at the bottom and also at the top. Of course, we'll find one of them will be under tension and the other one will be under compression. So basically, equations for a straight bar cannot be used for calculation of stresses in curved bar. So the derivation of equations are different, and that's why we have this experiment in order to compare the results between a curved bar and the last experiment of a straight bar. Longitudinal force, the force applied N, normally it will produce a stress of force over area, and then we will have another component of a stress will come from the bending moment. So I have two sides, side 1 and 2, top and bottom. I will have the value of M, which is moment, and then multiplied by some factor beta divided by W. W is the radial modulus of section of the bar, and beta, this is for section 1 and this is for section 2. Beta and alpha are some coefficients or factors depending on the ratio R1 to R2, outer radius and inner radius. So there is one table, this table 3.1 shows the values of alpha and beta compared to that ratio. So you calculate R1 divided by R2. If you find the ratio is 1.1, that means the coefficient alpha will be 1.003, beta will be 0.9693. And same thing, so we know that we have our R1 and R2 capital values, so we can easily calculate the value of alpha and beta. So the values of the total normal stress of point 1 and point 2, you see in this figure we have the experimental view of our specimen, and this is sensor number 1, point 1, and sensor number 2 for point 2. So basically we have two stresses. For point number 1, we will have the normal force, the normal stress force over area, and then we have the contribution of bending moment, where P is a force and R0 is a distance. So this will produce the moment, beta is the coefficient or factor, W is the radial modulus of elasticity of the cross section. Sigma 2 will be same values, but instead of beta we will take the other coefficient alpha, instead of negative we will take it with plus, because as I said before, we have one under tension and the other one under compression. And of course the mean value of R0 will be the outer radius plus the inner radius divided by 2, and alpha and beta calculated from table number 3. So the test specimen or the test piece is specimen number 2. If we go to the first table in the manual, you will see that specimen number 2 is this figure. We will fix it to have one force from this side and another force from this side in order to have the specimen under tension. The values or properties, dimensions of the specimen is outlined in this table. R1, outer radius, is given, the inner radius, width, height, modulus of elasticity, and of course calculated alpha and beta, and coefficient of sensors, always we have it 1. So yes, equations for theoretical calculations. The modulus, the radial modulus of section will be, it's similar to second moment of inertia. For a curved bar will be the thickness multiplied by the width square divided by 6. So based on that, sigma 1, the first stress, will be force, kilogram force, 2 Newton, so the delta B multiplied by 9.81 gravity divided by area, where area is B over B multiplied by H. Beta is the coefficient, the mean value of radius, and the radial modulus of section. So we can calculate sigma 1 and sigma 2, and note that this is negative and that is plus tension and compression. Equations for calculation based on the obtained data. So this will be based on the experiment or sensors. So to find the strain at position 1, we multiply the coefficient of sensor by the change in length, delta L, delta 1. The second point strain will be coefficient of sensor and delta 2. Based on that, we can find sigma 1, which is modulus of elasticity, multiplied by strain 1. For the second point, also sigma 2 is modulus of elasticity multiplied by strain number 2. Good. So if you want to prepare for the experiment and conduct the experiment, we have the steps described in this page. So the first one will be install the support 1. This is normal. We have support number 1, and we know that we can go back to our table in the first page of the manual to detail the numbers of each element. Support number 1, and we can fix it in hole number 8 and 9. So we calculate 1, 2, 3, 4, 5, 6, 7, 8, and 9 with the bolts, 10 millimeters bolts. Step number 2, we need to fix the support with lever. Support with lever, which is this element. We can fix it in holes number 1 and 2 with the bolts, and then lastly we can bring our specimen number 2 in the clamps of support 1 and 2. So we have these 2 pins fixed between support number 1 and support number 2, and this is the final shape of our experiment. When we apply a force in here, when we turn the knob to the right, we will apply some tension force, and then sensors 1 and 2 will be able to measure the elongations, and then we can calculate the values of stresses. So let's go and conduct our experiment in the software. Good. So let us install our specimen or our experiment. So going to the manual in Blackboard, we can see that step number 1 is to install the support. It has a number 1. So if you go back to the table of content or table of element, you can see that support number 1, it has a photo. This is the support number 1, and it's mentioned that fix it in holes number 8 and 9. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we should fix this in here. We have this bolt, 10 millimeter bolt. This is 1 and this is 2. Good. Step number 2, install the support with lever number 2. So this is element number 2, support with lever, and we should fix it in hole number 1 and 2. So this is 1 and 2, and we will fix it in here. This is hole number 1 and hole number 2 with the same bolts, 10mm bolts. Good. Step number 3, we use specimen number 2, which is the curved bar. You see, we will apply some force to test the stresses and strain on this curved bar. So we will fix it in this place here, but we need to turn the knob on right or left in order to have a proper distance, so we can go further. As you see, I need some space to have the pin fixed at this place. It's good now. What about the other side? No, we need more distance. Yes, I think it's good now. Yes. So now when we apply some force, it will be under tension from this side, and we need to connect the sensor for the measurements. So anytime we apply a force, it will be connected to this device. Anytime we apply a force here, the strain or elongations will be recorded by the sensor. So now let's go and perform the experiment. So for conducting the experiment, now you can realize that we are following almost the same steps, same as experiment number 1 and 2. Step number 1, assemble the test machine as described above. We already have our machine ready for the experiment. Number 2, make sure that we don't have initial load, so loosen the specimen by turning the knob on the lever. No load is applied, so we don't have any load, it's not under tension. Run the strength of material lab software by clicking the respective icon and select the third experiment, which is a study of stress state in a curved bar subjected to diametrically concentrated tensile force. So if I go to desktop, I will find the strength of materials software, third experiment, double click, and this is the platform of our third experiment. Same as before, this tab is for specimen parameters, the inner radius, outer radius, the thickness, width, and coefficient of sensors, the factors of ratio, R1 to R2, everything is detailed. Tab number 2 is for the table of increments and stresses. So when we make any readings, it will be shown in this table. And lastly, the specimen itself and the results or curves and the graphs. Good. So let's go back to our manual, enter the specimen data. No need to change anything because already we have the data given, and start the software panel. So if I go to the table of increments and I start, so now the experiment is ready and we can measure the values. We need first to put the meter on a force of 50 kilogram force. So I will apply some tension force until I reach 50 as advised, 49, 50, and I click measure. This is reading number 1, and then again go back to the manual, click measure. We did that. Increase an increment of 20, so I will go and increase another 20. That means I need 70 kilogram force, and also click measure, and that's it. So now from these two readings I can find the stress on the bottom and also the stress on top, and I have the curves readings from sensor 1 and sensor 2. If I want to look at the results, I will find that this is sensor number 1. That means data in blue is for sensor number 1, and this is sensor number 2, which is in red color. And this is the value of stresses. You know that this value is higher than that value, and one of them will be positive and the other will be negative for tension and compression. If I want to save this data, same as before, go to save. An Excel file will be generated. It's available in my computer, strength of material, Excel files, and this is our file. If I double click, you will find that data for inner radius, outer radius, everything, the readings that you have got for forces and sensors, and a table helps you to calculate the values of strains, stresses, and everything, and finally to compare the experimental and theoretical data. Yes, this will finish our experiment. The third experiment, which is a study of a stress state in a curved bar subjected to diametrically concentrated tensile force. And thank you.